Hello, everyone. Welcome to this special side event on day 3 of GEO Week. This is the session entitled A New GEO Map and Characterization of Global Coastlines. My name is Dawn Wright. I'm Chief Scientist of the Environmental Systems Research Institute, or ESRI, and I'm pleased to be moderating this session, which is about a project that all of us on this session have been involved in. This is a wonderful example of a partnership between industry, government, and academia. And there are many others who have been working on this project, on this global, standardized, high resolution data layer that shares with you the ecological settings of Earth's coastlines. But you're going to hear from a smaller group of us who have been leading this project. So I'm going to introduce them in order, and then we will start with the first speaker to share with you this amazing project and its resources. So I'm very, very, very pleased to be partnered with Roger Sayer, who is the Senior Scientist for Ecosystems at the U.S. Geological Survey within their Land Change Science Program. He also leads the GEO Global Ecosystems Mapping Activity, which has been in place since around 2014 to produce standardized, robust, practical global ecosystem maps for terrestrial, marine, and freshwater environments. And of course, we're going to focus on the coastal environment today. Also with us to speak is Keith Van Grafflin. He is an ESRI product engineer, and he's also the lead curator of ocean content for ESRI's Living Atlas of the World. We'll also be hearing from Kevin Butler, who is also a product engineer on ESRI's analysis and geoprocessing team, and he works as a special liaison to the scientific community in that capacity as well. We'll also hear from Laura Bachmeyer, who graduated recently with distinction from the Imperial College of London's Ecology, Evolution, and Conservation course of study, earning her Master of Science degree. She is now a full-time research assistant at Imperial College London, and she works on assessing the potential of seagrass for carbon sequestration globally and around the UK. And her presentation will talk about a very specific use case of this new global coastlines map and characterization. So we hope that you enjoy these presentations. We are going to be looking for your comments and questions, although we will not be able to respond to raised hands. But we hope to get to a very nice ending session, ending portion of this session to interact with you and your questions. So with that, I'd like to now turn the presentation over to Dr. Roger Sayer, U.S. Geological Survey. Roger?
Thank you very much, Dawn. That was a great introduction. Thank you all for your interest in our side event. As Dawn mentioned, I'm an ecosystems geographer at the U.S. Geological Survey, and I do map global standardized ecosystems for terrestrial, freshwater, and marine environments. I do that work under commission to GeoEco, as Dawn mentioned, and I always do that work in very close collaboration with ESRI by our shared interest in producing useful, global, where possible, geospatial content that will help us as a society face some of the global environmental problems that we are facing. Our session is an informational opportunity to share with you all a new resource that we produced from a recent high-resolution global segmentation analysis. We have produced what we call coastal segment units, or CSUs, and also ecological coastal units, which we call ECUs. And my job is to provide sort of a detailed introductory background on the concept and the method. And then we'll hear from Keith and Kevin, who will take a deeper dive, a closer look, and then we'll finish with Laura, who will give us an example of a real world application of the data, how she used and found the data. Okay, Keith. I have been engaged in GEO from the beginning and have for years led an activity in GEO ecosystems to develop these robust and practical ecosystems. And although I am the sort of official activity lead for GEO in this effort, Esri is really the spatial engine for developing the data. And that's after we always get together with teams of internationally recognized, renowned, really, subject matter experts to kind of figure out everything that we're going to do. And then we do it. And so in this slide, you see 4 examples of data layers that we have produced together under this GEO Commission. On the left, you see some recent work we did with the Nature Conservancy to produce a set of world terrestrial ecosystems. And I'm happy to say that TNC is now using this set of 431 world terrestrial ecosystems to help establish geographic priorities for where they should be working globally. On the right, you see a couple examples of some specific Earth surface features that we have mapped under this charge, namely global islands and global mountains. Keith? And here you see circled in red what we call the ecological marine units, or EMUs. Keith? The EMUs are a global, true 3D characterization of oceanic pelagic waters. We built the EMUs from 52 million points from the NOAA World Ocean Atlas resource. These cylindrical columns that you see here represent the long-term average values of several important variables like temperature, salinity, dissolved oxygen, and 3 nutrients. And the variable that you see represented here is temperature, where the pinker colors near the sea surface are warmer waters, and the colder waters at depth, at the sea floor, for example, are bluish. These EMU data are really rich, and we encourage you to check them out. However, they were not designed to capture variation in ecosystem diversity along the coasts. And so we knew we had to map coastal ecological settings independently. Keith? As everybody knows, there is an astonishing diversity in coastal ecological settings, as shown here, where, for example, just the geomorphology varies tremendously from rocky coasts to sandy beaches, coastal mountains, hexagonal basaltic columns, and even chalky bluffs. Okay, Keith? So to characterize that diversity, we took a coastline segmentation approach to analyze differences in coastal properties. This approach involved first developing a new 30-meter resolution image-derived map of Earth's coastlines, which we call the Global Shoreline Vector, or GSV. Then we segmented that GSV into 4 million 1 kilometer or shorter segments. We then attributed each of those 4 million segments with values from 10 variables that describe the ecological settings within which the coastline occurs. We then classified the 4 million segments into some 81,000 unique coastal segment units, CSUs. And for that classification work, we used the Coastal and Marine Ecosystem Classification Standard, or CMEX. And then finally, we also clustered the 4 million segments into ecological coastal units, the ECUs. Okay, Keith. Thank you, Keith. The 30 meter global shoreline vector is the spatial backbone and the source of line work for the global segmentation analysis. And here you can see the global shoreline vector really as a set of 5 continental mainland polygons in a tan color. And then there are thousands of island polygons, only the very biggest of which you can see here in green. We produced that global shoreline vector from a cloud-based interpretation of the year 2014 annual composite Landsat imagery. And then we used it to make a definitive map of Earth islands. Keith? So after segmenting the global shoreline vector into 4 million 1 kilometer or shorter segments, we attributed each segment with values from 10 ecological settings variables, which are depicted in the map graphic here. And those 10 variables included waterside properties, the ocean attributes, landside properties, the land attributes, and properties of the coastline itself. Okay, Keith. The classification of the segments produced 81,000 unique coastal segment units, the CSUs. And now here you see a pop-up result from a query of the data. This particular 1 kilometer segment from one of the Channel Islands off the coast of Southern California is classified as follows, if you can see this: sloping, straight, medium erodibility, warm temperate dry climate, low river discharge, moderate wave energy, moderately tidal, euhaline, oxic, and moderate to cool waters, clear, and low chlorophyll. So that was a mouthful. That's how it works. There's a lot of very rich attribution here on these CSUs. That's how it works. Any coastal segment anywhere in the world except Antarctica can be queried in this manner. And because the data are standardized, information is easily shared and compared with an apples to apples consistency. Okay, Keith. Now, this graphic shows the results of the statistical clustering of the 4 million segments into a total of 16 clusters. Each cluster is called an ecological coastal unit, or ECU. The ECUs represent 16 groups of coastal segments that are globally similar in the aggregate ecological setting, which is described by those 10 variables. Okay, Keith. And here is a look at a couple of individual ECUs. And this is ECU number 1, which you can see has a tropical distribution and is found on all 5 continents. Keith? In contrast, here is ECU number 16, which has a more cool temperate or boreal distribution, and very interestingly, seems to be characteristic of multi-island archipelago systems. All right, Keith. Now, this question of CSUs for ECU versus ECUs, in case you're a little confused, the CSUs are descriptive, and we consider them a global inventory of coastal ecological settings. And we hope that they have utility at local scales, as we believe that a 1 kilometer stretch of coastline is indeed an appropriate granularity for many management applications. The ECUs, on the other hand, are exploratory and preliminary. We think that they'll have utility for a variety of global assessments, such as the Convention on Biological Diversity Agenda, the Sustainable Development Goals, the IP-BESS activities, etc. And very importantly and very sincerely, we invite feedback from the community on the veracity and the utility of both the CSUs and the ECUs. And we really look forward to working with you on this resource. Keith? Now, is there any way, easy way to explore the data? Is there a tool that allows you to kick the tires without actually having to buy the car and download all the data? Yes, there is, and it's called the Global Coastline Explorer. And you can see here the welcome page for the Global Coastline Explorer. It has an awful lot of pertinent information. And if you click the link there, you will go to the web map. Now, please note the MBON, the GeoBON MBON logo in the banner screen. MBON has been a collaborator in this work, and two of the very MBON co-chairs, Frank Muller-Carger and Mark Costello, are also co-authors on our publications. Okay, Keith. So you click the link and you enter the web map, and all the usual functionality, the pan, the zoom, the query, displaying the data on a different base map, displaying the data on top of satellite imagery, which is always very nice to see how our shoreline lays up against the shoreline that you can see in the imagery. All that functionality is available. And so at this point, you zoom into your area of interest, Keith. And here we have zoomed to Puerto Rico, and we queried a 1 kilometer length of coastline on the island's southern shores. And there you have all the results, all the CSU properties, as well as what ECU that coastline belongs with. Okay, Keith. So for take homes, we have new management appropriate coastline data, which is intended to be useful for researchers, managers, communities, and policymakers. And there are so many potential applications, too many to list here. You will see some of these potential applications in the presentations that follow from Keith, Kevin, and Laura. We have papers for you. We have data. All of the papers, the data, and the tool are free and in the public domain. They're available through Esri's Living Atlas. And we really encourage you to check out these resources. And please don't hesitate to contact us for any reason at all. Keith? And here's a list of some of those resources. Keith. And that was my setup piece. And again, thank you for coming to our side event. Thank you for your interest in the global segments data. And now I will turn it over to my colleague from Esri, Keith Van Graffelen. Take it away, Keith.
Thanks so much, Roger. I appreciate it, and thank you for leading us through this project and giving us the opportunity to present here today. Today, I'm going to do a little bit on the data exploration side for these ecological coastal units. And to get us started with that, we've prepared a video of these ecological coastal units and exploring them around the globe. And I'd like to kick us off with that video. There is audio that's embedded here, so if you like that, enjoy. Great. I hope you enjoyed that video, and I'm going to switch back here to the presentation. And really, I hope you enjoyed the tour of ecological coastal units throughout our world and seeing what the different CSUs are as well. So there's a lot of data here, right? So there's a lot of information that can be gleaned from ecological coastal units, and that's what I want to explore with you today. So Roger mentioned there's over 4 million 1 kilometer segments, and they really are fascinating to explore and zoom into coastal areas that you're familiar with or curious about. And the Global Coastline Explorer is a great application to be able to do this. It allows that exploration and discovery. And there's these feature layers in ArcGIS Online, and there's an ArcGIS Pro package that allows you to access this information and do further analysis, investigation, query of the data to really learn more. These resources are made available to the GIS community through the ArcGIS Living Atlas of the World. Today, I want to do some of that further exploration with you and demonstrate a few opportunities to understand and summarize the ECU data as a whole. The idea here is to encourage the exploratory side of ecological coastal units. In this example, we can better understand the distribution of CSUs within ECU clusters. So how many of those CSUs are within each of these ecological coastal unit clusters, those 16 clusters that we have. And within this graph, we can see those 16 clusters, and we see that there's a relatively even distribution. We see that ECU 12 has the most CSUs, and ECU 9 has the least amount. But relatively, the distribution appears to be relatively normal. This map in the supporting graph explores the diversity of ecological coastal units within 10-degree latitudinal bands. So in this example, we notice that at the higher latitudes where we have greater areas of landmass or greater landmass, there is a greater distribution of the diversity of ECUs. So up here between 60 and 70 degrees north, we see that there's 13 different ECUs within that 10-degree latitudinal band. And this is just a way to look at the ECU data set as a whole, right? So this is not, it's very just exploratory to understand the data set a little bit better. And along the same line, we can look at the variance by latitudinal band. And we see between 40 and 50 degree north, there's a really high variance that we see within that. So maybe this is a more complex shoreline within these areas. But this is something that would encourage me to look a little bit deeper in those areas and really start to learn more about what in particular is happening. And then from a management standpoint, what countries have a higher diversity of ecological coastal units. And in this representation here, the cylinders represent higher ECU distribution by country. And really, it's no surprise that the countries with more shoreline have greater distribution of these different ECUs. So countries like Canada, United States, Russia, Greenland, Japan, and Argentina have numerous ECUs that make up their coastline. So just happy to be here today, happy to encourage you to explore ECUs a little bit deeper. I hope these are good examples that can spark your interest and get you thinking about how to do that. And I encourage you to reach out to us to learn more and engage with us. We want to help you. We want you to use these. And now I'd like to pass it over to Laura to talk about the work that she's been doing with ecological coastal units. Oh, excuse me. Actually, I'm going to play a video from my colleague, Kevin, before I get to Laura, about some of the analysis that he's done with ECUs as well. So here we go.
Thanks, Keith. As I was preparing to share this vignette today, I was struck by the powerful words of our session description. Coastal flooding, inundations, and sea level rise threaten infrastructure, economies, ecosystems, communities, and cultures. A fairly bleak picture. However, our session chairs, I think with a sense of optimism, have challenged us to find equitable solutions to these problems and proposed a framework for us moving forward. By stating adapting to these threats will require a holistic, coordinated, multi-sector approach to identify and implement transformative solutions. Today, I thought we'd explore together one example of how we hope the ecological coastal units and the coastal segment units on which they're based might help facilitate that holistic, coordinated approach. My thesis is this. A holistic coordinated approach will require a common framework or common language around which collaboration and coordination can be built. There's an adage in the conservation community that I think rings true here. You cannot manage or protect something that you don't know is there. It's our hope that the ECUs and the CSUs will provide, at least in some small way, a common language for describing coastal settings, and that these uniform descriptions will facilitate collaboration and cooperation on efforts to both protect and mitigate our coasts from the ever-increasing threats that they're facing. So along those lines, let's explore Mexico's largest and newest protected area, the Vizcaíno Biosphere Reserve. Located on the peninsula of Baja California, it spans from the Sea of Cortez to the Pacific Ocean. We'll focus on the Pacific coastal portion of the reserve today. To give you some idea of the scale of the coastal segment units, this map shows a portion of the peninsula northwest of the Bahia Tortugas. The black dots are the midpoints of each of the 1 kilometer segments, and the transects run perpendicular to the coastline. These transects were used to calculate the seafloor to land slope profile. If you recall from Roger's introduction, over 4 million of these 1 kilometer segments globally allow for some what I think fairly spatially granular descriptions of the world's coastline. We'll explore a few of these variables that each CSU has been attributed with here in Vizcaíno. The distribution of vegetation and terrestrial ecosystems in the coastal zone, as elsewhere in the terrestrial domain, is primarily controlled by temperature and precipitation. Even in this relatively small-scale exploration in Vizcaíno, there is diversity in the temperature precipitation regimes. The area is dominated by subtropical desert or dry landscapes. However, there are small niches of the warm temperate regime. Substrate erodibility is an important element of the ecological setting of a coastal area. Relatively erodible substrates are the source of materials characteristic of depositional environments like beaches and estuaries, whereas relatively inert substrates are associated with rocky coasts. Vizcaíno is dominated by highly erodible substrates composed primarily of unconsolidated sediments. However, there are pockets of medium and low erodible substrates. In the coastal zone, wave energy is a key determinant of marine physical environmental structure, really through its influence on erosional and depositional processes. There's some slight attenuation of wave energy within bays and estuaries in our study area, but when using the global classification of mean significant wave height, the entire study area would be described as having low to moderate wave energy. Tidal activity is an important hydrodynamic driver of coastal zone ecology. It mediates salinity levels, nutrient availability, temperature, root zone aeration, carbon flux, all of these ultimately influencing species distributions. While we see some slight magnification of tidal energies in bays and estuaries, the entire area would be classified as moderately tidal. In the coastal segment units, we use chlorophyll as a proxy variable for representing primary production. Vizcaíno is oleotrophic and mesotrophic. While each of these variables alone is interesting, I think the real power comes when we combine them into a consistent, plain language description. The 1 kilometer segment of shoreline highlighted here could be described as sloping, straight, high erodibility, subtropical desert with low river discharge, moderate wave energy, moderately tidal, with euhaline oxic warm to very warm waters that are clear and have low chlorophyll. I can also summarize the coastal segment units for our entire study area by taking the means of the continuous variables and the majority for the categorical variables for the coastal segment units that comprise our study area here. I can take that composite description and produce a similar plain language description of the entire study area. Here we can describe the west coast of our study area as having sloping, highly sinuous coastline exposed to low wave energy and moderate tides in a subtropical dry climate adjacent to clear, warm to very warm waters with moderate chlorophyll, normal salinity, and moderate oxygen. These consistent, plain language descriptions are an important first step, I think, in linking experts from numerous disparate disciplines with one another and with coastal communities to facilitate that knowledge exchange and promote cross-sector collaborations. While descriptions are useful, we can actually even go a little farther. Since we have a consistent set of attributes that describe the coastal setting for every 1 kilometer segment of the globe, we can start to do some apples-to-apples comparisons. I've used a technique called Coastline similarity to look at all of the 4 million plus coastal segment units globally in order to identify the area on the planet that is most similar to Vizcaíno. This technique identified an area in southern Brazil, and I've summarized the attributes of Vizcaíno in this table in the leftmost column, and for that region that was identified as the most similar region, I've summarized its attributes in the right-hand column here. So I think this is really more than just an interesting data science application. Finding areas with similar coastal settings based on the 10 attributes of the coastal segment units, we hope will spawn collaboration and lead to a sharing of mitigation strategies and promote that very important and necessary cross-sector collaboration. Thank you, and back to you, Roger.
Okay, thanks. Thanks a lot, Kevin. Kevin was not able to join us as he is on a plane at this very moment. But now we're going to pass it over to Laura Bachmeyer. Laura, it's all yours.
Yeah, thank you for passing it over. And yeah, hi, everyone. It's really great to be here today to talk to you about the work I've been involved in over the last 2 months in collaboration with Imperial College London. And so I started this project for my master's thesis, and I'm currently trying to develop it further within a research assistant role. And the main focus of our project has been to investigate factors affecting organic carbon storage variability within seagrass meadows. And today I will not only be sharing my work with you, but also demonstrating how the ECUs can contribute to global coastal habitat studies. Next slide, please. So as you can see here on this graph, global increases in temperature have been linked to rising CO2 levels in our atmosphere for some time now, as most of you will probably know. And since then, the global community has focused on finding new ways to counteract human emissions using things like nature-based mitigation strategies, which traditionally focus on things like reforestation. And then more recently, efforts have turned to what's known as blue carbon, which includes all coastal vegetative ecosystems. Next slide, please. And I specifically focused on the role of seagrass meadows within that. So seagrass meadows are some of the most widely distributed global coastal ecosystems, as you can see here on this map. And they also provide a range of ecosystem services in addition to their role in nutrient cycling, such as storing organic carbon. And blue carbon ecosystems store majority of their carbon in the sediment layer rather than the vegetation. And here it can be efficiently sequestered, which means to be removed from the atmosphere permanently. If sediment layers bury the carbon, and microbial communities which live in that sediment don't respire that organic carbon back into CO2. Unfortunately, the roots of seagrasses create anoxic environments where very few microbes can survive, allowing them to act as carbon sequesters. But how effectively they do this and what factors control higher carbon storage is still very much debated. Next slide, please. Next slide, please. And so yeah, this is the, one back. There you go. And so yeah, this is the aim of my study. So the first goal was to develop a global database encapsulating all available organic carbon measurements from the literature, and then to add as many environmental variables as possible to this. And during this step is where the ECUs came in, and they provided a lot of the necessary environmental data. But yeah, more on that in a bit. And then secondly, I then wanted to develop a few different models to try and link these environmental variables to higher carbon storage. So to assess which variables are responsible for the variation in organic carbon. And this is an essential step if seagrasses and other blue carbon ecosystems are to be integrated into global carbon budgets. And there's been a lot of great work done on advancing the blue carbon field recently, with one other attempt so far that has also tried linking environmental variables to high carbon storage. And this study focused on Australia with a more focused data set. And so my hope really with this study was to build on that, sort of have a global scale and add additional parameters. Next slide, please. And so as I mentioned, the first step of my project was undertaking a literature meta-analysis to collect data on global organic carbon measurements and corresponding environmental factors, with all final sites shown here on this map. And from the literature, I was able to add around 100 environmental variables. But because all these studies focused on differing aspects within seagrass blue carbon research, I ended up with a database with quite a lot of missing data, with actually around 70% of all environmental variables being incomplete. And this meant I could still try and build some predictive models, but they would have to be partially based on imputed data, which would decrease the accuracy of the results and not really show a very realistic picture. And this would have been an issue, as organic carbon has shown to be extremely variable across spatial scales. And so exact environmental data is really essential to assess this variability properly. Next slide, please. One back, please. So to give you an idea of this variability, the average amount of carbon of my global database was around 114 megagrams per hectare, with tropical regions having a slightly higher average than temperate. And looking at the minimum and maximum of the organic carbon found in global seagrass sediments, the range is also really large. And then additionally to that, seagrass species richness also varied between regions, with tropical regions hosting a lot more species, which you can see here based on these box plots. So on the right-hand side, there's just a lot more species found in these regions. And what was really interesting was that the same species, which are differing storage amounts depending on the climate, with Posidonia oceanica, which is here circled in red. And if you go to the next slide, that's what the species looks like, has the highest organic carbon storage in temperate regions, but the lowest in tropical. And so in order to try and explain some of this variability, a more complete and precise environmental data set was needed. Next slide, please. And so yeah, this is where the ECUs came in. And actually not only those, but I ended up using 3 products from Esri, the ECUs, the EMUs, and a ARC web map with data on global shipping ports, and which I used as a proxy for level of disturbance, so distance of a seagrass site to the nearest port. But the ECUs were by far the most critical addition, not only because they focused on coastal areas, which is where all seagrass meadows exist, but also because of their high spatial resolution. And in total, all 3 of these products were able to add around 44 environmental variables with almost no missing data to the data set. And for the final models, I actually mainly used variables from all these three products, with a few added from the literature which had more complete data, but mostly I focused on these. Next slide, please. And so yeah, I just wanted to take you through some of the important variables that each of these products added to my study. So the ECUs mostly added data on marine physical variables such as mean wave height, tidal range, etc. And just to give you an example of how these might impact seagrasses, so the turbidity of the seawater will determine how much sunlight can penetrate that water column, which then directly impacts the primary production of seagrasses, or how much organic carbon that meadow can produce. And then the EMUs focused more on marine nutrient variables such as temperature, salinity, dissolved oxygen, etc. And one example of how these might impact carbon storage is dissolved oxygen directly impacts the metabolic rate of seagrasses, and again, therefore, their primary production. And then finally, the global shipping port data added information on human disturbance. So boating, mooring, and anchoring increases mechanical destruction of seagrass meadows and leads to increased erosion of sedimentary organic carbon. And not only that, but also it increases pollution in these areas, so including hydrocarbon emissions and oil leaks, which is shown to have adverse effects on seagrass health. So yeah, after collating all the data from the literature, I extracted the corresponding environmental data using the nearest neighbor algorithm. And this allows for two layers to be joined based on nearest neighbor relationships. So what this means is that each seagrass site has a corresponding latitude and longitude, and these will be joined through this algorithm to the midpoints of the nearest feature of these geodatabases, therefore extracting the most spatially accurate environmental value for each site. Next slide, please. And so yeah, after collating all this data, it was actually time to analyze it. And here I used a random forest regression, which is a supervised learning algorithm and is appropriate for large data sets with a mix of continuous and categorical data, non-parametric distributions, and it also accounts for predictor variable interactions. So it was really a perfect fit for both the data and the aims of this project. And I'm going to try and explain this as quickly and painlessly as possible. So random forests assemble a multitude of individual decision trees. So these are these triangular tree-like things you can see at the top of this graphic here. And so what the algorithm does is basically it iterates the model many, many times. So each dot on these trees represents an individual iteration of the model. And each time it iterates it, it will remove or add randomly one of the environmental variables, and then it checks whether the model performance has improved or not. And this process allows us to assess the importance of each variable in contributing to the variation in organic carbon. And then the final step is it takes all these trees and takes an average across them to get a highly accurate overall model. And then to evaluate the performance of the final models, I used three different measures. I firstly used what's called R-squared, which represents how much variance in percent within organic carbon is explained by that model. I also used what's called the mean absolute error to assess prediction accuracy of the model. And what this measure does is it calculates the difference in organic carbon from the actual seagrass site within the data and what the model predicts for that site. So basically, it's the error within the model's estimations. And then I lastly also used the increase in node purity to assess the importance of each individual parameter. So this measure assesses the increase in prediction accuracy of an individual model due to the inclusion of that specific variable. And yeah, so finally, in terms of experimental design, I constructed a model for all global data for temperate and then for tropical regions separately, as the carbon data demonstrated this divide between the bioregions. Next slide, please. So yeah, the results from the global model showed a large mean absolute error and a low R-squared, which means that even with the inclusion of all these environmental variables, the empirical model was not really able to explain much of the variation within organic carbon. And as you can see by the graph here, so this graph shows how important each variable is in explaining the variation. And country, species, distance to port, maximum slope, and a marine physical environment measure were all primary factors. And just to explain this a little bit, so maximum slope combines the width and grade of the intertidal zone, so it represents local topography or seafloor topography. And the marine environment measure is an integrative measure of sea surface temperature, oxygen, and salinity, which was also provided by the ECUs. Next slide, please. So assessing the outcomes from the temperate and tropical models separately, the predictive accuracy goes down in temperate systems, meaning that organic carbon is even more variable here. And then, sorry, next slide, please. And then in tropical regions, it actually had the highest predictive accuracy based on having the lowest error, and it also had the highest amount of variance explained with that model. So even though these results weren't that great, what was great about the outcomes of all three of these is that the top variables didn't really change between the models much, so we could reliably interpret these as being quite important. So specifically, maximum slope and distance support seem to have a really high impact. Next slide, please. So yeah, overarchingly, the study highlights significant differences in organic carbon and seagrass species between bioregions. So tropical regions store more organic carbon, as I mentioned in the beginning, which makes sense considering primary production is higher due to higher irradiance in these regions. And they also host more species. And this is a phenomenon not unique to seagrasses. So one of the main hypotheses for this is that tropical regions, due to more stable conditions, has allowed for faster speciation rates. And environmental stability also favors higher carbon storage due to a decrease in perturbations, risking remineralization, so less storms and things like that, sort of mixing up the sediment and releasing the carbon. And then finally, differences were also found within the same species across the two regions. And the hypothesis here is that local environmental pressures and habitat settings favor different sizes. So therefore, some species will be very efficient at storing organic carbon in variable temperate conditions due to their physiologies, but then it's not so optimal for stable tropical conditions. Then in terms of the results from the models, they all indicate really fine-scale regional variability, which was really highlighted by country as the #1 factor. The problem here is that country could really be seen as a proxy for a number of other factors such as climate, coastline, management strategy, and even quality of data. So what it really highlights is just the need for more site-specific assessments. The hypothesis for the importance of both maximum slope and the marine environment is that both have over thousands of years shaped how individual ecological features exist and interact, and therefore they both sort of delineate these environments into small-scale microhabitats. So for example, the width and grade of the intertidal zone will impact how sunlight and the tides interact with the seagrass meadow. And then lastly, anthropogenic stressors, especially distance to a port, also show to have a high impact, demonstrating that humans are negatively impacting the carbon storage capabilities of seagrass meadows. Next slide, please. So yeah, as I mentioned, the project is still ongoing, and at the moment I'm hoping to advance the modeling by using clustering methods to assess the variability on a smaller scale. I'm also hoping to find a way to use some of the sediment information I have in the data set to make inferences about its importance, as this is an aspect that's still sort of missing at the moment from the models. And then lastly, me and the team have been fortunate enough to be financially supported by Ocean Conservation Trust, who I will be joining in the spring for a few weeks to collect some of my own data with the aim of assessing intra-site variability. And this is an essential first step in producing more reliable blue carbon budgets. And yeah, I'm also hoping to focus a PhD on this next year, as there is really a lot left to be done. And I want to end the presentation with thanking Roger Sayer, his entire team, and especially Esri for supporting my project. And again, I want to emphasize how critical the ECUs were in its development. So these sorts of products represent an accessible, affordable, increasingly reliable source of data for environmental sciences. And in my opinion, will play a key role in tackling some of these big challenges still ahead. And then on a final note, here are my contact details and the names of my collaborators. And please get in touch if you have any questions, just want to chat about blue carbon or want to collaborate in any way. And yeah, thank you for listening.
Thank you, Laura. May I have a word here, Don, and we'll turn it over to you for closing.
Go right ahead, Roger.
Okay, Laura, that was great. And your presentation ended with some ideas on future work, and it got me to thinking, oh, I needed to mention to everybody, one of the very big things we're doing in terms of overall future work is we're going to start a new collaboration with UNEP WCMC, the World Conservation Monitoring Center, as really the keeper of a lot of the biological assemblages data, because we got a lot of feedback, initial feedback that said, these are great units, but we would like to know what are the biological assemblages associated with these 1 kilometer coastlines. For example, are there mangroves there? coral reef seagrass beds, as Laura studied, shellfish beds, kelp forests. And so we're going to work with WCMC to add some rich biological assemblage attribution to our coastal segment data. So be on the lookout for that. And having said that, now I'll pass it to Dawn.
Thank you, Roger. We are out of time for this wonderful session. We have given you a treasure chest full of resources. Unfortunately, we have no time left for questions, but I did put in the chat a web link where you can obtain all of the resources that were touched upon in this session. And we will all four of us, try to be in the Esri booth that's associated with this side event for more questions and interaction. So thank you so very much for attending, and have a great rest of your GEO experience.
Thank you, everybody. And with that, I will officially end the session. So again, thanks for coming. I hope you can check out the resource. Take care, everybody. Bye-bye.